All right, so on mole conversions, this is where dimensional analysis is really important. And what you want to do is you want to be diligent about labeling units. So I went through before and just reminded you of the way we do this with Avogadro's number and molar masses. You get molar masses off the periodic table. So for number one, pretty straightforward. We have 0.0504 moles of Na. You want to get in the habit of not just writing moles, but moles of what? And you'll see as we progress why that becomes important. And we want to get to atoms here. And an atom is a particle. So that means all we have to do to go from moles to particles, we'll just use Avogadro's number. Avogadro's number has whatever you want in the numerator. Whoops. See, when you talk and write at the same time. It's whatever per mole, just like a dozen is 12 per mole, or sorry, 12 per dozen. And I was telling someone else, you guys as a group did quite well on your scratch paper as far as showing your work. A few people just had random numbers floating around, but most of you were very organized, which makes my life easier, but more important, it makes your life easier. All right, so this should, don't forget about sig figs. This number has 3, so I get 3.04 times 10 to the 22nd. You want to make sure, this is where calculators will start becoming an issue if you're doing things wrong. So make sure you can get the same answers as me. That's number one. Okay, number two, 78.95 grams of cobalt. And we want to go to moles of cobalt. So here we want moles on the top. And we want grams of cobalt on the bottom. So even if you're not sure what to do, grams and moles, that's what a molar mass is. It's a mass of a mole. And so we want the number on the periodic table goes with grams. Cobalt is 58.93. Somebody asked me how many sig figs. If your periodic table goes to 2 decimal places, that's fine. I gave you one that goes to 2 decimal places. You should usually carry molar masses at least 1 more decimal place more than you're asked, but if you only have 4 sig figs, you only have 4 sig figs. And so I get 1.340.
Recording in progress.
I'm sorry, thought I heard something. All right, number 3, I'm gonna move this over just a little bit more. Maybe I won't. Okay, number 3, we have 5.68 times 10 to the 27th iron atoms. And here we want grams of iron. So we don't know the mass of a single atom. So again, you can go forwards or you can go backwards. I'll go forwards this time just to show you. So we want, if you don't know what to do, let's get rid of that unit. We want atoms on the bottom. We can only relate atoms to moles. So we know that 1 mole of iron is Avogadro's number. So for the next test, you should definitely have Avogadro's number memorized. But I think by the time you go through homework 4, you'll memorize it without even trying. All right, and then now we want grams from moles, and iron is 55.85. Again, always cancel as you go. So the habits that we got from the unit conversions, now you're going to use them for chemistry. And this is where a calculator, if you're having calculator issues, it'll show up right now. So make sure you can get the same answer as me. Let me do it one more time because I was talking. Let's put this one in the scientific notation. So I have 3 sig figs, 5.27 times 10 to the 5th. All right, so if you got 10 to the 50th or something, you're doing something wrong with your scientific notation on your calculator, and I can help you with that. All right, number 4. It's just a little
Professor, for that one, is it okay we write down the whole number instead of putting it in scientific?
You want to write 52700, all those zeros you can, but you really want to get in the habit of
Yeah,
starting.
but I just need to grab my wallet out of my bag.
You get your water?
No, I'm not my wallet.
Yeah,
Those
so
are my bag, but
make sure you
I
guys
want
are,
to have it in my bag before Vegas. That's what I wanted to get.
Yeah, don't eat the quick. And I'm
Oh, watch out for the bag. Sorry, you looked at it a little bit.
there we go. All right, let's mute. All right, so number 4.
Sorry, a question for number 3.
Yeah,
I understand how to do this, but can you explain why? Because the mass that you have in the periodic table, isn't that per atom?
it
But
is.
why would you have to
No,
convert?
no. The mass on the periodic table is grams per mole.
Oh, okay.
It's AMUs per atom, but an AMU is a stupid unit. So it's grams per mole.
Oh, okay, I see. So you would have to convert to moles and then a gram.
That's why you always got to go through moles.
Okay, thank you.
Okay, so we have 9.58 times 10 to the 22nd water molecules, and we want to go to moles of water. Yeah, periodic table is always grams per mole. All right, so we're going particles, water, a molecule is a particle, to moles. So it's similar to number 1, but it's backwards. We want moles of water in the top. And we have Avogadro's number in the bottom. So dimensional analysis tells you if you're going to multiply or divide. I always write out the word molecules, but you could just write H2Os if you want. 9.58 times 10 to the 22nd divided by Avogadro's number. All right, so I get 0.159. Squeeze one more on here and then we'll start erasing. All right, so number 5.
Professor, for that one, does 0.16 work or?
Well, then we 0.160.
Okay.
Yes. Yeah, if you're off by 1 or 2 in the last decimal place, that's fine, but make sure you have 3 sig figs. Okay, so 0.0558 moles of MnO2, and we want to go to grams. So here we can't just look up the molar mass, we have to calculate it. So Mn, the way I'll just do this one time because I did it a lot in the videos. There's 1 Mn, there's 2 oxygens. Don't confuse Mn and Mg. Manganese is 54.94. Oxygen is 16. So that's 32. That's 54.94. So when I add these up, is 86.94. All right, so that means we have 86.94 grams of MnO2 per mole of MnO2. Okay, times 0.0558 is 4.85 grams. All right. So I think you can see how important it is to really label those units. All right, so let's go to number 6.
Quick question.
Yes.
Why is it only 3 significant figures?
Because 0.0558, that 0 is not significant.
Because it's a placeholder?
Yep. Also because if you can think of it that way, which is correct, right? If you covered it up, it's 0.558, which is very different. Also, remember, zeros are significant if they're after a significant figure and after a decimal point, but there's no significant figure in front of it. So either way.
So if there was a 0 in front of that,
Oh, that's
both
zero.
zeros would be.
If you have like 0.05, this 0 here is completely irrelevant. That's just to help you see the decimal point better.
Okay, thank you.
So number 6, 87.20 grams of zinc chloride. So I'm not going to go through the steps on calculating the molar mass again, but you want to verify for yourself that you can get those molar masses that I'm coming up with. So this is going to be ZnCl2 molecules. So again, I'm going from grams to particles. I'm going to do this one backwards just to show you the different way of thinking it through. But you can do it, learning how to solve problems backwards is really powerful. So if I don't know what to do to start, working it backwards, I know I can get molecules using Avogadro's number. So I don't care if you think it forwards or backwards, right? That's kind of internally how you do things. But if you can work them forwards and backwards, it just makes it more powerful for you, because then if you get stuck one way, you can try it the other way. All right, so now I've got the right unit in the right place. Now what I need unit-wise is I need moles of ZnCl2 on the top. And I need grams of ZnCl2 on the bottom. And so that should be, aha, that's the molar mass. So then you look it up. And so I get 136.29 or so. Let me double check it. Yep, 136. All right, and then you see how the units work. And so we do the math. So we get 3.853 because this 0 is significant. Times 10 to the 23rd. And if you're getting atoms or molecules, you should always get a big number, like 10 to the 20th or something like that, 10 to the 19th, because there's always going to be a large number of atoms or molecules. All right, let me just go to here, scroll this up a little bit. Okay, number 7, we have, and no matter whether you're thinking forwards or thinking backwards, you should always, always, always think of it like a map, like we did with unit conversions. Write down what you know. So we're going to start at 0.825 moles of FeBr3. And we're going to go to, so always write down the units of your answer. Write that right away, just so you don't answer the wrong question. All right, so we have moles of FeBr3 and Br atoms. So these are different substances. So what I need to do, let's go backwards, because where am I going to get atoms? Well, I can get atoms from Avogadro's number. There's 6.022 times 10 to the 23rd bromine atoms in a mole of bromine, like that, right? Now you see moles of bromine and moles of FeBr3 do not cancel. So this is a good example of why don't just write moles, but moles of what? Because if you just write moles here and don't write the Br, and you just write moles here, and you won't realize that these aren't the same thing. And you won't realize that you have another step here. We need moles of Br on the top and moles of FeBr3 on the bottom. And then you can see from the formula, right? The formula is good for one molecule. It's also good for moles. So there's 3 moles of Br in a mole of FeBr3. How do we know that? Because that's the meaning of a formula. So again, this is one where it's really important to not just write moles, but write moles of what? 0.825 times 3 times Avogadro's number. So I get 1.49 times 10 to the 24th. All right. Okay, now number 8, we have 2.50 times 10 to the 3rd. So number 8, 2.50 times 10 to the 3rd. Whoops. Trying to, one more try. Grams of Al2SO4 So that subscript, and we want to get to aluminum atoms. I'm going to move this over now. I want to get to Al atoms. So mine may have a little bit more space. All right, so we can go forwards, we can go backwards. Let's go, we'll do this one forward a little bit. So I need to make grams go away. So this one, I'm gonna need the molar mass of this mess. So let me just, so the molar mass of this, the 3 distributes to, so I have 12 oxygens and 3 sulfurs. Now, if you wanna know why isn't it written S3O12, when we do nomenclature, you'll see why that is. But for now, we're just gonna use the formula as is. So we have So I got 342.14. Hopefully someone else did that and got the same number. So I have 1 mole of Al2SO4 for 342. That seems right. 14. All right, so again, it's 2 times 26 for aluminum, 3 times 32 for the sulfur, 12 times 16 for the oxygen. So now that's gone. Now we have moles of Al2SO4. We want Al atoms. All right, so again, let's say we need atoms. If we don't know what to do here, we know that there's Avogadro's number. Per mole of Al, right? And you see, again, these moles don't cancel. So what we need is we need moles of Al on the top to cancel that. And then we need moles of Al2SO4 in the bottom. And from the formula, there are 2 moles of Al in a mole of Al2SO4. Make sure your units work. Now we'll do the math. 3 sig figs. All right, so I get 8.80 times 10 to the 24th. I'm going to erase this down here now. All right, let's look at number 9. What's number 9? Percent oxygen in Al2SO4. So this one's a little different. This isn't really a, whoops, I just did. Let's try that again. All right, so 9, we want the percent oxygen in this compound. Now the thing about a formula is good no matter how much. So it doesn't really matter how much of the compound, the percentage, it's percent by mass. So we want to get grams of oxygen over grams of Al2SO4 3, and then of course times 100 to make it a percent. Now we know, so we'll just do it for 1 mole. Make it easy for 1 mole, because the percent's the same no matter how much. We know that 1 mole of Al2SO4 3 is 342 grams, because we calculated that up here. Otherwise, you'd have to calculate it. But we know 1 mole is that. The grams of oxygen, this has 12 oxygens in there. So for the grams of oxygen, oops, it looks like it says go. I see that there's a, what's up in the chat? Actually, let me answer your question about Avogadro's number in a minute. Avogadro's number was calculated. We want grams of oxygen will be, well, there's 12 oxygens times 16 grams per mole. So 12 times 16 is 192. So it's 192. Okay, this kind of stuff, just give me 2 decimal places. Sig figs are kind of out the window on this. Just go to a couple decimal places. All right, so that's 56.12%. Yeah, the question in the chat was, is Avogadro's number just an arbitrary number? And no, it's not. I don't know where the word, I looked up where the word mole came from, and it's kind of weird. It's kind of hard to figure it out exactly. But Avogadro's number was calculated. And it was, you can calculate it a number of ways. You can calculate it through the gas laws called Avogadro's law. You can calculate it. There's a lot of different ways. We used to actually do a lab where we tried to calculate it, but it's a little tricky. So it actually was one of the, most physical constants are calculated. They're determined experimentally, and they said, well, every time we put these things together, we keep getting the same number. All right. So I hope that answers that question. Last one, I think, is we have, so number 10, let me just write it here. We have 1.75 grams of sulfur, and we got 4.37 grams of a compound. Damn it, 37. I'm going to call it SXOY. We want to come up with that formula. Now, we haven't done a lot of chemistry in terms of coming up with, you can get the oxygen just by subtraction by law of conservation of matter, and it combined with oxygen, so the rest of it has to be oxygen. So that means the oxygen is going to be 4.37 minus 1.75. So there's 2.62. All right, so we want to come up with the empirical formula of this. Let me just draw a line here. So to come up with the empirical formula, we want to get the formula of this. We need to know what X and Y are. And by the way, what element do you write first? If you look at the periodic table, the one either further to the left or lower down is written first, and that's just kind of they had a meeting. All right, so the first thing we have to remember, a formula is a mole ratio. So let's convert each to moles. 2.62 grams of oxygen. So 1 mole of sulfur. And we'll just go to 2 decimal places, 32.06 grams of sulfur. 1 mole of O is 16 grams of O. So this is 0.0 here, 0.0545859. And this is for the sulfur. And then the oxygen, 2.62. Actually, I carried an extra digit, so we'll just 546 divided by 16 is 0.164. We'll just call it 0.164. All right. So then what we do, so if we were to stop now, we can't stop now, but we would have a formula of S.0546 0.164. And that ratio is correct, but we can't have fractions in a formula because this is good for one molecule. So the trick is, how do we keep the ratio the same, but make them into whole numbers? Remember, from a ratio, you can multiply or divide these two numbers by whatever you want, and the ratio would be the same. Meaning we could multiply each of them by 12, and the ratio would be the same. We could divide each of them by 38, and the ratio would be the same. But what we're going to do, we're going to make this one into a 1. So let's divide each by 0.05459. Really, just 0546. But I'm keeping an extra digit just because I was. So this is now 1. And this is 2.999. So this is 3, actually. It comes out to be a 3. All right, so this fell right out. So this is SO3. In the videos and the slides when I went through this, sometimes you'll get a fraction here, like a 1 and a 1.5. Then what you do is you do the same thing again, but you multiply. But this one came out just nice and clean like that. So if you look at the ones I did in the one, I think I did at least 1 in the video. I might have done 2. I did one where there's an extra step. All right, what I'm going to do before I open it up to questions, I want to stop the recording, and then I'll open it up to questions. That way your questions won't be recorded. Because let me stop the recording.